So today I'm going to talk to you all a bit about optical tools for the characterization of plasmas and their dynamics. First, I'm going to just give you a bit of a quick overview. First, going to discuss a bit what sort of information we actually want out of plasmas, and then what techniques we typically use to characterize our plasmas, and then the challenge, what the actual imaging challenges are that underpin trying to characterize the plasmas. And then I'll look at some of the requirements that we have then in terms of actually measuring and observing plasmas. And then I'll give some examples of how modern cameras can be used to characterize plasmas. I'll start with some lab-based examples and also some examples of how some of our cameras have been used in Fusion to actually to look at and monitor plasmas that have been formed there. So first off, in the characterization of plasmas, what are we interested in? Well, typically, we probably want to know, well, we may be interested in the chemical makeup of our plasma, the structure of our plasma, how our plasma evolves temporally over time. We might want to look at the electron density of our plasma or the electron and ion temperature of our plasma. And so typically, how do we normally do this? Well, there's several choices. We may be looking at time-resolved optical imaging. So, for instance, actually physically watching how the plasma evolves over short lifespan. It could be of the order of nanoseconds or picoseconds. We could be doing spectroscopy on our plasma, which is obviously quite a big one. We could be doing UV-Vis, optical emission spectroscopy, XUV, X-ray, PLIF, Thomson scattering, just to name a few. I mean, obviously there's very many different types of spectroscopy that we typically use to characterize our plasmas. So in particular today, what I want to focus on is maybe sort of two main tools that we use when looking at plasmas. And those are intensified CCD or CMOS cameras or EMCCDs. So I thought not necessarily knowing exactly how much everyone knows about intensified cameras, I'll just give a quick sort of overview just to make sure we're all familiar with this, with these and how they work. So at the core of an ICCD is an intensifier tube. Originally, these were developed for night vision. And basically, ICCDs just, they take a low flux of photons that are detected, and then they multiply them up to and apply a gain to make the most out of low light imaging conditions. Hence, these were originally used for night vision. And how these actually work in practice is, well, if you take your typical gated camera, in the front section of your camera, you'll have an intensified tube, and your incoming light will pass through an input window. It'll then hit a photocathode, which converts the photons to photoelectrons. This then allows the camera to gate, and this is how we achieve our ultra-fast time-resolved imaging. And your photoelectrons then pass through the microchannel plate of the camera. This multiplies up the photoelectrons through impact ionization. And your photoelectrons then collide with your phosphor screen, which then transfers them back into visible photons, which are then conducted through some kind of coupling, normally a fiber optic coupling, down into your sensor with your two-dimensional CCD or CMOS sensor to then allow you to take your image. So that's just a quick overview, just so we're all on the same page. And quite an important part of this, and I mentioned briefly before, is you achieve your ultrafast gating through pulsing the voltage in your photocathode. And because if you, depending on the voltage you apply across this dictates whether or not the photoelectrons you've created reach your MCP and therefore pass all the way through the setup and are detected. So one important part of when looking at an intensified camera is the photocathode that you select. There's generally 3 different types of photocathodes that you can have on an intensified camera. Generation 2 photocathodes, so as you can see on the spectrum on the right-hand side, these offer quite a good broadband response from 125 to 900 nanometers. However, their quantum efficiency can be somewhat limited, and they can be somewhat resistive, and so they can struggle to get below 10 or hundreds of nanometers sort of gating speeds. However, there are generation 3 photocathodes that are maybe more suitable for visible to near-infrared, just because they're deposited on glass as opposed to sort of a metallic underlay like generation 2 photocathodes. And this can allow them to, gate down theoretically to, hundreds of picoseconds in terms of time. And their peak quantum efficiency is significantly higher, up to even like 50% in some cases, compared to generation 2 photocathodes. And lastly, there's also in-gas image intensifiers, which are slightly more specialized, but these allow you to really access the near infrared. And these are suitable up to 110 nanometer, 1,100 nanometers, and these can be gateable down to nanoseconds. So, and though the quantum efficiency of some of these photocathodes can be relatively low, it's worth bearing in mind that because you're going to run these through a microchannel plate and multiply up your signal, even with a low quantum efficiency, you can still get a strong signal to noise ratio depending on the gain you apply. So, sort of maybe one of the next most important parts of your intensified camera is the actual sensor. Then you have fiber coupled at the other end, and typically you would either have a CCD or an SCMOS sensor for this. CCDs, read out every single pixel at a time. These can be mainly used for, low rate imaging or high rate spectroscopy. They can be, typically for CCD, you'd expect to image at a few hertz. And with multi-track spectroscopy, obviously, you can achieve much faster frame rates. However, they can be somewhat limited in their frame rates, and you may not get every repetition if, for instance, you're using a high repetition rate laser to generate your plasmas. SCMOS technology, on the other hand, does allow you to achieve much faster frame rates, and you can have fast multi-track spectroscopy as well. And it also gives you high dynamic range and high speed, which it can be quite complementary depending on the intensity of the plasmas you're generating. So these are sort of the two sensor types you would have with an intensified camera. Another option for imaging plasmas is EMCCD cameras. EMCCD cameras are similar to CCD cameras. However, after the readout register, you have an extra register, which is called the gain register, in which through impact ionization, your photoelectrons that you're reading off are multiplied up and then read off, which allows you to achieve much better signal to noise ratio than typically you would find in a CCD camera. And you can achieve relatively high frame rates with EMCCDs, and they do have single photon sensitivity. So here I've just got a picture on the right-hand side which illustrates the difference between, a CCD camera which has no gain applied and EM gain applied, and you can obviously the image is visibly much clearer. So just want to talk a bit now about the sort of some of the challenges that come with time resolved plasma imaging. And I'll start with imaging first and then talk a bit about spectroscopy afterwards. So when you're trying to image your plasma, there's several sort of challenges that you're confronted with. Firstly, and obviously depending on what you're doing, but often you can have an ultra-fast plasma that doesn't hang around very long. So to actually capture that in an image, you need some kind of ultra-fast nanosecond gating. So in this image in the top, for instance, this was captured using a series of ultra-fast gated images sequentially added up to give you a full kinetic series. Typically also, if you were trying to acquire a large kinetic series of some kind, you may be actually acquiring, hundreds or thousands of frames and stacking them together. And so typically to do that with a camera to make the most out of your, laser pulses or what have you, you may require a fast frame rate to actually then reduce your experimental time and to make the most of everything you're doing. Thirdly, what can be quite challenging can be oversaturation of the sensor, because plasmas, such as, for example, dielectric barrier discharge plasma, can have a significant variation in optical intensity across the surface of the plasma. This can mean that your sensor may be oversaturated in some areas and undersaturated in other areas. So to avoid this, the camera should probably have quite high dynamic range to allow you to resolve both of these within a single frame, instead of having to take, two different images at different gain levels, for instance. On the other hand, you may have quite a low light intensity. If you've run your signal through a spectrometer, for instance, and you've lost some light, or depending on your setup, this can be quite a barrier to overcome. So here's where some kind of single photon sensitivity and adjustable gain can be very important. And lastly, depending on what you're looking at, you may be looking at a plasma that has some very fine structures, some kind of electrical discharge plasma. And so to fully capture that, you probably actually want quite a high resolution camera or sensor to fully capture that. So some examples of sort of plasma imaging and where it's been overcome, I thought I'd just show a few. So obviously I've talked about this plasma bulk kinetics example. But for instance, here I have an example of a transient discharge barrier transient dielectric barrier discharge experiment that was looking at how the emission profile plasma changes with gas flow, and you can see how well it's managed to be resolved. Here I've got an example of plasma stream dynamics in an underwater discharge that was captured by one of our Andor iStar cameras at the University of Loughborough. And here's an example of a surface electric discharge in atmospheric air, also captured by an iStar CCD. So those are sort of just a bit about plasma imaging. What I want to talk a bit more about now is plasma spectroscopy and some of the challenges about this, because obviously there's quite a bit more variety and maybe there's more different techniques you could use in plasma spectroscopy. So in plasma spectroscopy, you've got several sort of unique challenges. Firstly, you could be trying to resolve very fine spectra. So in order to achieve that, you'll need some kind of high spectral resolution sensor. You might be trying to maximize your multi-track input volume. And so in order to do that, you would want some kind of large area sensor to capture that. Also, depending on the spectroscopy you're trying to do, you might be trying to resolve, UV signals or even near IR signals. So getting the right kind of photocathode or sensor type in order to maximize that, it can be quite a key consideration depending on what you're trying to do. And as I mentioned previously, if you're trying to acquire large data sets, having high spectral rates will really help to reduce your experimental time, especially if you're trying to do some kind of maybe hyperspectral imaging or, depending on what you're trying to do. And obviously maximizing signal to noise, single photon sensitivity can be quite key to making the most out of, what could be a fairly faint signal. And lastly, if you're particularly if you're trying to do LIBS and some kind of spectroscopy, you want to shutter out any unwanted signal or excitation sources. And that's where it can be very helpful to have some kind of ultra-fast nanosecond gating to achieve this. So I've just got now a few more examples of where these sort of challenges have been overcome. And just it can be helpful, I think, to see examples of setups where people have done this. So my first example is this setup at the University of Madrid, where they were doing optical emission spectroscopy on a plasma that they'd generated, and they were interested in looking at how ionic species within the plasma decayed in relation to the neutral atomic and molecular species within the plasma. And they were also quite interested in how the excitation, temperature, and electron density fluctuated with time from the instant laser pulse that they had set up. So this was captured using an iStar camera. Next, I just have a quick example of laser-induced fluorescence. And in this particular example, the user had an ICC camera set up with two-line excitation lift to look at how the temperature profiles of sprays varied. And then they use this to compare their experimental data with their modeled data. And as you can see from the graphs on the right-hand side here, and as you can see, there's a little bit of variance between them. And nextly, I've got an example of where Thomson scattering has been used in plasma spectroscopy in a lab. In this example, a gated Andor ICC camera was used to measure how the electron density of an argon streamer varied through using Thomson laser scattering. They want to learn how the properties of the plasma discharge and electron densities varied throughout the streamer. And they found quite a strong difference between the electron density and the emission profile that they recorded. So next, I have a few examples of where some of our cameras in particular have been used in tokamak experiments and how they've overcome some of the challenges they found that are faced in these kind of imaging environments. So in this example here, they were interested in measuring how ion temperature and plasma rotation varied within the plasma, and they were using Doppler shift and Doppler broadening to do this. This was at the Compass Tacomac, and as you can see, they had their light coming in through their plasma, and they ran it through two objective lenses into a 2-grating spectrometer coupled to an Andor EMCCD camera. And from their data that they collected, they showed that the evolution of colloidal plasma rotation and ion temperature and how that changed over time within their tokamak. Yeah, as I mentioned, yeah, this was captured using an Andor EMCCD camera for its extra sensitivity. So next I have an example here where there was researchers interested in looking at how the ion temperature and electron temperature measurements within their plasma varied, and they're using Thomson scattering to do this. And from the data they managed to collect, they showed that the ion and electron temperature profiles obtained from this, how they changed over distance within their plasma. And from this setup, they had 2 optical fiber inputs, which were then bounce their light off a mirror through a lens, and then they put it through a diffraction spectrometer, and then they had an and/or EMCCD coupled at the end of that. Again, it was chosen for its high sensitivity because I think they weren't expecting too much light to come through their fibers. Here I have an example of where LIBS has been used on a tokamak reactor, and in this they were particularly interested at looking at how basically impurities gathered on the containment surface wall within the tokamak in between operation. And this data was acquired using another and/or iStar camera. And basically they took numerous LIBS scans of the surface of the panel inside the tokamak to identify the elements deposited. They were looking at the graphite limiter in particular to see what elements were building up there. And lastly, I just have an example of how an and/or spectroscopy camera was used as part of a setup in an X-ray spectrometer. And they were using this to look for ion temperature measurements. And in this example, they had this setup, as you can see on the left-hand side, where they had quite some X-rays coming out of the plasma, and they then bounced it onto a detector to then look at the spread of the different energy levels within their plasma, and from that they were working out the temperature. So yes, I'm sorry if I've spoken a little bit quick. I have a habit of doing that, but that's about all I have to say. So thank you very much for watching. We'll now take any questions you may have, or if you have any more longer involved questions that you want to ask me, please feel free to drop me an email at t.woodward@andor.com. And thank you for your attention.